Section 3.3, multi-class problems with softmax. The multinomial regression model, as it is known in statistics, or softmax regression, as it is known in machine learning, is the generalization of logistic regression from the binary response case to the case of k greater than 2 classes. Just a footnote. In some machine learning circles, this can also be called softmax logistic regression, or multinomial logistic regression, or multi-class logistic regression, or sometimes people just say logistic regression, but it's multi-class. Like logistic regression, we denote the training observations via d going from x1, y1 to xn, yn. Yet here, each label, yj, is one of k class values 1 through k, not just 0 or 1. The purpose of the model is to predict class probability vectors, or if used for classification, to predict a class in a multi-class setting. The model. Just like logistic regression predicts 2 classes and uses phi of x for the probability of positive response, multinomial regression predicts multiple classes. The predicted response is the probability vector. Note that this is bold, the probability vector, phi sub 1 of x up to phi sub k of x. So this probability vector. Where if we represent the random variables of the feature vector and the response via x and y respectively, as we did previously, then phi sub k of x is a probability of y being k given the features. And that's for every k. To compare 319 with 3.1, so 3.1 we'll go up to 3.1 briefly. So 3.1 was the logistic regression case where we only had a phi of x and a 1 minus phi of x for 1 and 0 respectively. So that was 3.1. So the more general multinomial logistic regression case, 319, observe that 3.1 is like 319 with k equals 2, where we take phi of x to be phi 1 and 1 minus phi of x to be phi 2. Okay, so it's going from 2 classes to k classes. No big deal. The name multinomial regression stems from the multinomial distribution, which is a probability distribution over vectors of length k constituting non-negative integers that sum up to some specified integer n. Specifically, some random vector y1 through yk follows a multinomial distribution with parameters n, where capital N is a positive integer, and a vector phi sub 1, phi sub k, and that's a probability vector. So its entries are non-negative and sum up to 1. If the probability of y1 being u1, y2 being u2, up to yk being uk is this multinomial coefficient, that's n factorial divided by u1 factorial times u2 factorial times uk factorial, multiplied by the product of phi k to the power uk, where k goes from 1 to k. Okay, so phi 1 to the power u1, phi 2 to the power u2, etc. This is for specific cases, for specific values in this probability mass function, where the sum of the values exactly equals n. And if this does not hold, then the probability is 0. Okay, so that's just a review or a description of what we call the multinomial distribution. A specific case of the multinomial distribution with n equals 1. So n equals 1 means that only one of these is going to be 1. Okay, and the other ones are going to be 0. all right, so that's n equals 1, is called the categorical distribution. In this case, the random vector y1 through yk is a one-hot encoded vector. So one coordinate is 1 and the other coordinates are 0. That is, it has a single entry as 1 and all other entries as 0. A statistical assumption in multinomial regression is that the one-hot encoded response given the feature vectors x follows a categorical distribution. So that's the main statistical assumption in multinomial regression. Namely, the probability of getting such a response given the features x is this multinomial distribution probability mass function. Now you might ask, where is this thing? But this thing is here. It is simply that n is 1, so 1 factorial divide, so you get there a 1 factorial, which is 1 divided by some 1 factorial, and all the other things are 0 factorial, which are all 1. So this whole thing is a 1, and hence we don't see it. Okay. So that's what we have. Where in this case, yk is 1 if y equals k, i.e. it equals 1 if y equals k and 0 otherwise. So long story short, we have a categorical distribution as the probability distribution. The key model assumption in multimodal regression is in the way in which the probability vector phi of x depends on the feature vector x. There are two possible parameterizations, which we refer to as the statistical parameterization and the machine learning parameterization. Okay, and this is our language in this book. So we called it the statistical parameterization or the machine learning parameterization. So slight variations. The former, meaning the statistical parameterization, presents an identifiable model, whereas the latter, meaning the machine learning parameterization, is slightly simpler but has some redundant parameters. Now, just a footnote, like logistic regression, this assumption is rooted in the theory of GLM, a topic that we refer to in the notes and references at the end of the chapter. So let's now look at the statistical parameterization. In the statistical parameterization, it is assumed that phi k of x, meaning the probability of, phi k of x plays a role here, right? So all of the phi k of x play a role together. Right? So phi k of x is the exponent of bk plus w sub k transposed x divided by 1 plus this summation over j. Okay, j going 1 to k minus 1 of the exponent of bj plus wj transposed x. And that's true for all of the k's except for the last case. So that's the statistical parameterization. Okay. And further, for the last k, for k being capital K, phi k of x is 1 minus all of these guys. Okay. So with the statistical parameterization, we get a probability vector phi 1 up to phi k, capital K, yes, where phi capital K is a complement of all of the other phi's, okay? And the assumption is how these phi's depend on your feature vectors x, and they depend via this form. We'll give this form a name soon. This directly generalizes a sigmoidal relationship of logistic regression 3.5 from the k equal 2 classes case to the k greater or equal to 2 classes case. So in the logistic regression case 3.5, let's look at equation 3.5 one more time. This was the assumption in logistic regression. The assumption in logistic regression was that phi of x, namely the probability of getting 1, that's in binary logistic regression, the basic logistic regression, was as follows. Okay, but now we have many k's, many classes k's, and multinomial regression generalizes that. And the statistical parameterization, which we're starting with first, directly generalizes that. With the statistical parameterization, the parameters of the multinomial regression, let's put this here, okay, are, so what are the parameters? They are all of the intercepts, but k minus 1 of them. Okay, so all of those intercepts. And all of the weights. Okay. But the weights are one set of weights. They're subscripted with this brackets in the subscript. The weights are, each one is a vector in their own right. So each intercept is a scalar. There are k minus 1 intercepts. And each vector of weights is a vector. So there are k minus 1 of those. And hence, the number of parameters you can compute is k minus 1 times p plus 1. Okay. So that's the total number of parameters here. Okay. Now, the scalar parameters b1 to bk minus 1 are bias intercept parameters, and each of the vector parameters w sub 1 up to wk minus 1 is a weight vector, and that's sometimes called a regression parameter. With this parameterization, we may also view the final bias weight vector wk as a scalar 0 and the vector 0 respectively. Okay, so there's no final bias vector and weight vector. Such a restriction on bk and wk allows us to combine 321 and 322 into, we can just write now as follows. So if we force the final bk and wk to be 0, then we can write everything in a neater form, which is as follows. Okay, so exponent of bk plus wk for k going 1 to k, and we all the time divide by summing over the j here. All right. Now you keep in mind that for the last capital K, when j equals capital K, then you have a 0 and a 0, and then this is a 1, okay? And this is also a 1. So this special last case falls out. Okay, so this special last case falls out of it, meaning it's generalized inside if you make this assumption. Now let's move on to the machine learning parameterization. And moving on to the machine learning parameterization, the last class also has free parameters, bk and wk, like the other classes. So we don't do this thing for the first class and then the last class. In this case, the parameter space is kind of simpler in a sense. It's rk multiplied by rp to the power k. And we have a bit more parameters. So k times p plus 1 as opposed to k minus 1 times p plus 1. Now, again, this representation is valid. So this representation is for both machine learning parameterization and statistical parameterization. Yet, unlike the statistical parameterization, the last term in the summation in the denominator is not restricted to B1. In this sense, the machine learning parameterization is simpler. However, when estimating theta with maximum likelihood estimation, there's never a unique theta that maximizes the likelihood or minimizes the loss. That is actually not a big deal, and it makes things simpler. Okay. The Softmax function and multinomial regression as a shallow neural network. A common function in deep learning, especially when considering classification problems, is the function from Rk to Rk. It's a vector input, vector output function, vector of the same size. Softmax activation function. So we call it an activation function in this book. So for some vector z, which is z1 through zk, the softmax applied to z is you exponent each of the coordinates and you divide by the sum. So that's what you call a softmax. Softmax and its derivative expressions are further discussed in section 5.3, 2 chapters from now. At this point, let us just point out that for any vector z in Rk, the result of softmax is a probability vector. And let me say just a bit more. So softmax takes an arbitrary vector that does not have to be normalized, or a probability vector can have negative entries, positive entries, etc. Sometimes these entries, you just call those inputs logits. And what softmax does is it creates a probability vector from that. Now, with softmax defined, we can revisit the multinomial regression model 324 and represent it as a softmax of a vector of length k that has this affine transformation b sub k plus wk transposed x at the kth coordinate. So more succinctly, multinomial regression is simply this view, where what we do is softmax of this very neat form, the bias vector plus the weight matrix w times x. And you can call this guy inside z, that's an element of Rk. And after you apply softmax, you can call this thing A, that's activation. Where y hat is the prediction of bold phi of x, as in 318, and the k-dimensional vector B and the k by p dimensional matrix W are as follows. So B has all the biases, and W has each one of the rows of W is one of those guys, which we had here before. Okay, so W has these rows. So compare 326 with 315 of logistic regression. So 326 was our nice representation of multinomial regression. And let's go to 319. Sorry, maybe it was with 315. And this is the representation for logistic regression. So in logistic regression, you only have binary output, so you don't have a softmax, you just have a sigmoid, so you will use the sigmoid here, okay? Whereas in multinomial regression, we have a vector output in general, so we do a softmax. But it's the same thing, really. In the logistic regression case, Z is a scalar, and so is A. In contrast, in the multinomial regression case, the affine transformation converts a vector x in Rp into a vector z in Rk. So p is a number of features and k is the number of labels. And then the softmax activation retains the same dimension to arrive at A. Note also that 326, so equation 326, or this form 326, is valid both in the statistical parameterization and the machine learning parameterization. In the former, meaning in the statistical parameterization, the last bias bk and the last row wk of 327 are set to zeros, right? So when you do the statistical parameterization, you force this to be zeros and you force these guys to be zeros. Okay. With the latter, they are free variables. This representation positions multinomial regression as a shallow neural network, similarly to the way logistic regression is a shallow neural network. The difference is that multinomial regression has vector outputs, while logistic regression has a scalar output. Figure 3.6 illustrates a multinomial regression model as a neural network. Here, each circle can again be viewed as an artificial neuron. However, note that the softmax activation affects all neurons together via the normalization in the denominator of 325. 325 is our definition of the softmax function. Okay, so softmax operates on all of the elements, but not one by one. At the end of the day, you have to normalize by the denominator. We'll see the figure in a second. Hence, the activation value of each neuron is not independent of the activation values of the other neurons. So let's look at this figure. This is a figure of multinomial regression. So this is your, in a sense, one way to represent a shallow neural network. So you've got inputs x1, x2, x3, up to xp, okay? Each one of these guys is a neuron. Okay, and again, neurons have, people mean different things when they call neurons in neural networks. Right? So first of all, you've got your affine transformation in each case. So that's B1, the bias, plus W1 transposed X. So all of the X's go inside. You've got your affine transformation. And you've got your B2 plus W2 transposed X. And again, right? So each neuron has its own bias scalar and weight vector. All right, and then you get the affine transformation. Then you get your Z1 and Z2 up to ZK. So that's great. After you do this on all the neurons, you're now, and look at this dotted circle we put here, because everything kind of works together. Because then these guys, you can call them logits, okay, in some formal way. We don't write this in the book, but so they're often informally called logits. Okay, logit values. And then you take the exponent of each one and divide by the sum of the exponents of everything. So then what you have here, A1, A2, up to AK is actually a probability vector. And that yields to you your estimate of the probabilities, and all this thing together is Y hat. Okay, so that's our multinomial regression neural network, which is a shallow neural network with a softmax at output. Likelihood and cross entropy. Now that we understand the multinomial regression model, both from a statistical perspective using the probabilistic interpretation 320, and as a deep learning model using 326, okay? So 320 again, sorry. So 320 equation 320 was, well, this is what we mean by these probabilities. Okay, it should really be 320 and 321. And the machine learning representation is 326. Let us consider the maximum likelihood estimation and equivalently the loss function minimization. So we still didn't speak about the loss or cost for this network. To obtain an estimate theta hat using maximum likelihood estimation, we repeat similar lines to the development of logistic regression. Specifically, the likelihood of the model for the data D is defined as in 3.7. So we already had a likelihood expression 3.7. Now using the probability law of the categorical distribution, so probability law of categorical distribution is 320, we obtain the likelihood. So what we do is because observations are assumed to be IID, we multiply over all observations the probability rule for each case. So where we use the parameter space theta as in a statistical parameterization. Right, so theta is your parameter space in statistical parameterization. So now considering the log likelihood, similarly to the development for logistic regression, by applying log to this guy, we obtain the summation over all observations, the summation over all classes, and this indicator of the observation label actually equaling label k moved down outside of the log. Okay, so that's just logarithm rules. And now we can observe that for each observation I, only one of these indicators from all possible k's is going to be 1. And the rest are going to be 0, right? Because observation only equals k. So then you can just represent this summation as log at the entry. Instead of k here, I'm putting y sub I. Right. So that's kind of neat. So it's not a double summation, it's now a single summation. And now log of phi sub I of x is, remember, it was your softmax expression. So you've got your exponent in the denominator, and you've got it here, minus, the new exponent in the numerator, minus the log of the denominator. All right. In the second step, we use a subscript yi because except for the index k, where y equals k, all other summands of the internal sum of the first row are 0. So that's what we did. And the third step follows from 324, and 324 is just going to be this representation of the softmax of the affine transformation, which we had here before we actually called it a softmax, but it's a softmax of the affine transformation. Okay, so we've got the likelihood expression, the log likelihood expression. Now, similarly to our development of logistic regression, Emily, in equation 310, that was for the binary logistic regression, we can represent the problem as a minimization problem and define the estimator via argmin of take again, because you want to do maximum likelihood, so you want to maximize this thing, so it's minimize the negative of this thing, and we throw in the 1 on n just to agree with the paradigm of loss minimization we have for other neural networks. Further, similar to the development of, so let's keep this equation here. Further, similar to the development for logistic regression, one can also view the problem as a loss minimization problem, whereas before the losses of the form, this general representation of a loss, where Ci is a loss per observation, based on the expression of the log likelihood 328, okay, so this is the important expression for the log likelihood 328, and using yi for the vector phi of xi, the loss for an individual observation is now, so the loss for an individual observation is this thing, which is negative log of yi. So I guess we're actually using this one. Okay. So notice that you have log of your predicted value, which would be a probability at the index of the label. The first form above arises from the first line of 328, and the second form is from the second line. The expression on the right-hand side of 329, the expressions in the right-hand side of 329 are in fact called categorical cross entropy. So we had before the binary cross entropy, but now this expression here is called the categorical cross entropy. More precisely, for a label y in 1 through k and probability vector y hat of length k, we define the categorical cross entropy as this summation, negative of the log of the probabilities multiplied by this indicator. And since all of those indicators are going to be 0, except for a single one of them, which would be 1, and that's for y equaling k, we can just write this as negative log of y hat. Y hat is a vector, okay, remember, at the coordinate y. Where the final expression y hat y means taking the element at index y from the vector y hat. We thus see that the CI, that's the individual loss for observation I, is a categorical cross entropy. Now we'll relate this to logistic regression, binary logistic regression. We've already seen the binary cross entropy in equation 312. Like it, the categorical cross entropy 330 is the empirical estimate of the cross entropy of two probability distribution appearing in equation B1 in appendix B. So you can look at appendix B. We note here that in many contexts of deep learning, one just uses the phrase cross entropy without the prefix binary or categorical. Then the distinction between CE binary and CE categorical is based on context and the type of arguments y and y hat. So you'll see if y and y hat are binary or if y is a vector or a 0-1 scale. In the former, y is a binary outcome in 0-1 and y hat is a scalar probability. In the latter, y is a multi-class choice 1 through k and y hat is a probability vector of length k in 0-1k. The binary cross entropy is a special case of the categorical cross entropy. Okay. And you can this is just kind of tying things together. It's not so important, but you can do the binary cross entropy of y hat with y either 0 and 1 and y hat in the range 0-1. That can be represented as CE categorical. You can actually do 2 minus y and put in this vector. Okay. If this interests anybody, if anybody's digging between the difference categorical and binary, then you can find this insight here. Just as footnotes also important for practitioners. In practice, when deep learning systems implement binary and categorical cross entropy, then you use log of u plus epsilon, where epsilon is a false small fixed parameter, and this allows to seamlessly include probability u equals 0 as an input. Okay, back to here. It may be useful to also see other notational forms for the loss of an individual observation CI. Making use of equation 326, let's just also see. So equation 326 again was this nice form for multinomial regression. Okay, that was equation 326. So making use of equation 326, we can say that the loss for an individual observation, CI theta, is categorical cross entropy of the label and softmax applied here, where we parameterize theta to be composed of the vector B and the matrix W. Namely, theta is now like that. Alternatively, it's also good to have this form if you would like. And you can compare 333 to the last line of 328. Okay, so these are just different forms of this loss, which you will see. In particular, when we're going to take derivatives, this last form is important. And here we are, derivatives and learning. Like logistic regression, inference for multinomial regression can be efficiently carried out using second-order methods. Nevertheless, like logistic regression, when multinomial regression is viewed as a deep learning model with very large P, one often uses gradient descent, first-order optimization, in place of the second-order methods. We now present the derivative expressions of CI. These expressions allow one to use gradient descent just as in the case of logistic regression. So using either the statistical parameterization with d equals k minus 1 times p plus 1 parameters, or the machine learning parameterization, which has p plus 1 more parameters. So that's a machine learning parameterization, just a bit more wasteful in parameters, but a bit neater. We have, but it doesn't have a unique solution for the MLE. We have that theta equals b comma w consists of both a vector b and a matrix w. Thus, in dealing with the gradient of CI, of the individual cost for observation I, with respect to theta, denoted gradient Ci theta, one needs to either vectorize theta into a vector of length d, so you can take that vector and weight matrix, just want to make one long vector, okay? Or alternatively, to make use of the derivative of real-valued functions with respect to a matrix is defined in Appendix A. So specifically formula A6 in Appendix A. You look, oops, jump to the way to the top. So you could look at formula A6 in Appendix A if you would like. Sorry, just get back to this. We are here. Our presentation uses both variants, and it is a prelude for further derivative expressions involving matrix-valued parameters in, oh, I see, I'm clicking on it and then it jumps, in chapter 5. Sorry about this. Okay, we continue. And the chapters are full. So let us first consider the derivative of 333 with respect to the individual scalar elements, theta equals BW. Okay, so just let's recall what 333 is. So as I said, this form of the individual loss form observation is going to be useful for derivatives, and we can take the derivative of this with respect to individual elements of the parameters, okay, the vector B or the matrix W, right? So take derivative of that. So we can see by using differentiation that d of this Ci with respect to the kth coordinate of the bias is going to be this expression. And we can see that d of Ci with respect to the kth element of the weight matrix is going to be this expression. Okay. So these expressions are very similar, with except the difference being that, sorry, in the expression for the weight, we also have the XL in there, and not for the bias. These derivatives can then be placed in a d-dimensional vector to form this gradient. Now, observe that the expressions above involve the softmax function, where the ratio of the exponent with the sum of the exponent in this expression is a case coordinate of the softmax. Okay, so each one of these here, you've got the softmax, and you're taking the case coordinate. That's because of this k. Okay, and similarly here, that's the case coordinate of the softmax. Okay, because of this k. Note that in the numerator in both cases, we're summing up over j. Okay, it's a bit subtle, but you can investigate it. This hints at simpler expressions, and indeed we may use unit vector notation, EJ, in place of this indicator, okay, to obtain that by vectorizing this overall k, we've got this expression. So this is the softmax, that has become the softmax. And here you've got the unit vector at the y-ith coordinate. And similarly, the other expression is the same, only that now we're going to multiply by xi transposed. And let's just do a sanity check for dimensions. So here you have a derivative of a scalar with respect to a matrix. So you would like this to be a matrix, and this is a vector of length k, and this is a row vector of length p. So this outer product is a k by p matrix. Okay, and W is also a k by p matrix, right? So if we look at W, the matrix W, which we have here, it's a k by p matrix. Okay, so you've got p features and k labels. It all works out. With such a representation, the first expression, which is a derivative with respect to a vector, is in fact composed of the coordinates associated with the bias vector b of the gradient. Further, the second expression is a derivative of a real valued function with respect to a matrix, as we just said, which we represent using the notation of A6, that's an equation in Appendix A, to represent the matrix with kth element denoting that. So it's just a matrix of derivative entries. In general, when one implements gradient-based optimization, as in step 3 of algorithm 2.1 of chapter 2, so that was a basic gradient descent algorithm where we actually need to compute the gradient, or using one of multiple variance presented in chapter 4, so many algorithms in chapter 4 need to use the gradient, these derivatives need to be used with the right shape dimension taken into account. We also mentioned that it's sometimes common to subsume the bias terms expressions within the weight parameter expressions by augmenting the feature vector to be of length p plus 1, and then you don't have a bias anymore. Where the first feature is a constant 1, so then if you'd have a constant 1 here, it's just like having a 1 here, and it's the same. Good. This practice was already used in linear regression treatment of section 2.3 and could have been also employed in logistic regression treatment of section 3.1. However, we mentioned that from a deep learning perspective, the weight parameter W often receive different treatment than the bias parameters in B, and thus keeping B separate from W notationally is instructive. Okay, that's a subtle issue. Note that like logistic regression, the loss minimization problem of multinomial regression is convex. And thus, with proper hyperparameter choices, example learning rate, a global minimum can in principle always be reached. We establish, meaning prove, the convexity of this optimization problem in the next chapter. So still, multinomial logistic regression is very lucky in the sense that we have these gradients, and we also have Hessian expressions, and they're explicit, so we don't need to use automatic differentiation or backpropagation. Not that automatic differentiation is bad. I mean, that's what makes deep learning work. But for this shallow neural network, things are still very standard. Okay. Classification with multinomial regression yields convex polytope decision regions. Whoa. Recall that with multi-class classification, our goal is to provide a prediction y hat, so that's an actual index, for the label 1 to k associated with the input feature vector. In section 2.2, that's in the previous chapter, we introduced concepts of binary classification, and then via the example of the linear model in section 2.3, we saw strategies for adapting binary classifiers to multi-class classifiers. Right, so there we spoke about if you have binary classifiers, how you can use them to make a multi-class classifier. This was via the 1 versus rest and 1 versus 1 approaches. In contrast to these approaches, the multinomial model provides a direct solution for multi-class classification, since the output y hat is already a probability vector over 1 to k. This approach is also common in more complicated deep learning models presented in the chapters that follow. So instead of kind of having main and binary classifiers and tying them together, we have a multi-class classifier from the go. In general, an output vector y hat, which is a probability vector, can be used to create a classifier by choosing the class that has the highest probability and breaking ties arbitrarily. Namely, we do this very simple and intuitive thing. We say our chosen label y hat big Y is going to be the class with the highest probability. This approach is called maximum a posteriori probability, MAP decision rule, since it simply chooses y hat as a class that is most probable. It is the most common decision rule when using deep learning models for classification. You don't always use it though. As a side note, for binary classification, a map decision agrees with binary classification threshold prediction 2.5 with a threshold of tau equals 0.5. So back in chapter 2, we had equation 2.5 where we said if the probability is less than tau, you choose 0. If it's greater than tau, you choose 1. So map is like with tau 0.5. And similarly to fine-tuning the parameter tau, in the multi-class case, we may also deviate from map decisions and adjust 334 if needed. As an example, consider figure 3.7, so here it is in front of us, that represents a map-based rule applied to the output of a multinomial model trained on n equals 17 synthetic data points. So we have 17 synthetic data points with p equal 2 features. So p equal 2 features, we can plot them in a plane, and k equals 4 classes. Okay, so each feature is colored red, blue, green, or gray based on the class. Like the binary classification example of figure 3.2, so we had one like that in figure 3.2, this multi-class classification example illustrates the output of y hat x star for any x star in RP. So these are these kind of decision regions, okay? So each one of these regions, okay, that's, you can take any x star, any arbitrary x star in RP, any x star, and have these regions. That's these colors that you see. Similarly to the logistic regression case, we observe that the decision boundaries are straight lines. This is not a coincidence, but rather a property of multinomial regression. And that's the title of the section, right? Classification with multinomial regression yields convex, polytope are these intersections of half spaces, decision regions. So here we establish this property. So denote by C sub k the set of input features vectors x such that y hat x equaling k. So given a model, when is this map decision rule going to give us y hat equaling k, big Y hat equaling k? We now see that CK is an intersection of half spaces, and that's what you call a convex polytope, and that's why you get these straight lines. To see this, consider some arbitrary point x in RP and fix some class label k. We can now compare y hat k of x star and yj hat of x star for all other labels j. Specifically, since the denominator of the softmax expression is independent of the index, so in y hat you have in the denominator, you have a softmax, right? The softmax of the affine transformation. The denominator doesn't care, it's just a summation. So just to see this so you remember. So the denominator of the softmax doesn't care on the label, and here, right, this is a softmax. This is independent. There's no k here, no k in this denominator. Let's go back. The denominator of softmax is independent of the index. So you'll have that y hat k is greater than y hat j if and only if the numerators are bigger. So if and only if this is greater than this, and then you can just apply log to this, and then you'll have that that's happens if and only this plus this is greater or equal than 0. So we see that this comparison defines a hyperplane, and we'll call this hyperplane H sub kj, and here's an equation for this hyperplane. And we see that this holds if and only if the hyperplane is greater or equal to 0 for all those classes j. So now y hat x star equals k if it's greater than all other j, and hence we see that the decision rule, the space, the region in RP, which we call C sub k. So this is like C sub 1, and this is C sub 2, etc. Okay, this is C sub 4, and this is C sub 3. Okay, these C's, C sub 4 is closed, and the other C's are open in this case. All right. So we see that that's an intersection of k minus 1 hyperplanes, and that's why we get this form. And finally, as a concrete example, we return to the MNIST, remember the digits classification explored in section 2.3. In that section, we used the 1 versus rest and 1 versus 1 strategies because we had binary classifiers, and we used a linear model to build linear model-based multi-class classifiers. So see table 2.1 in chapter 2, where we present confusion matrices for these classifiers when trained on 60,000 MNIST test images and tested on the 10,000 test images of MNIST. We now report the performance of multinomial regression on this data set, as well as the application of one versus rest and one versus one with logistic regression. Okay, so now we have all these other approaches to use. So the summary is in this table, okay, in table 3.1. And I should say that some of these numbers are still in question as we're making this video. So look at the final version of the book and you'll see perhaps an update to some of these numbers, because some of these numbers might not be precise based on the experiments that we ran. So our purpose with this comparison is not to claim which method is best, since in practice, all these methods are significantly beat by some convolutional neural networks as presented in chapter 6, but rather just to highlight that there are different strategies, okay? So let's look at the strategies. So we can do linear regression, one versus rest. This was in chapter 2. We have 10 models. We have linear regression, one versus one. You have 45 models. Or 90 models if you're sloppy and you don't do an IJJI, you take different models. Now you can also do a logistic regression, one versus rest. It'll give you 10 models and you get 45 models. And here you have the number of parameters, and they're exactly the same for linear and logistic regression. Now finally, you've got multinomial regression. Multinomial regression is inherently designed, multinomial logistic regression, okay, is inherently designed to deal with multiple classes. And here you've got the test accuracy in each case, but again, these numbers need to be updated. Okay, so I thought that was a very exciting section. So you saw a simple, shallow neural network with softmax, which is a very important concept in deep learning. And in the context of statistics, it's called multinomial regression. Machine learners sometimes just call it logistic regression, even though in our book we call logistic regression to the binary case only. So you saw that, and that concludes our section 3.3. As always, let us know what you think. Leave comments below, and thank you for watching. Thanks. Bye-bye.